Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here's a problem for today. This is written answer section, problem number 5 from the last exam MLC from fall 2017. Fred and Molly are age X and Y respectively. They have just purchased a special joint life 10-year term insurance with a death benefit of $100,000. The death benefit is payable immediately upon the simultaneous death of Fred and Molly. It is also payable immediately upon the death of Fred if Molly dies first. There is no benefit payable if Fred dies first. Net premiums are payable continuously at the annual rate of P while both Fred and Molly are alive, and at a rate of 0.75p after the death of Molly. The contract is priced using a force of interest of 6% and the following common shock model. Here's the picture of that common shock model. We have states 0, 1, 2, and 3. State 0 is when both Fred and Molly are alive. State 1 is when Fred is alive, Molly is dead. State 2 is when Fred is dead, Molly is alive. The force of transition from, and state 3 is when they're both dead, I'm sorry. And state 0 is, a force of transition from state 0 to state 1 is 1% of 0.01. To state 2 is 0.014, to state 3 0.001. The force of transition from state 1 to state 3 is 0.012, and the force of transition from state 2 to state 3 is 0.016. For part A, our job is to show that the probability of transition from state 0 to state 1 in t years, or t units of time, is 0.01 over 0.013 times the quantity of e to the minus 0.012 t minus e to the minus 0.025 t. For part B, we need to show that the expected present value of the death benefit on simultaneous deaths is 670 to the nearest 10, and we should calculate the value to the nearest 1. For the second part of part B, we need to show that expected present value of the death benefit payable if Fred dies after Molly is 360 to the nearest 10. We should calculate the value to the nearest 1. Then for part C, we need to show that the premium P equals 150 to the nearest 10 and calculate the value of the nearest 0.1. For part D, we need to show or calculate the net premium reserve at time 5 given that only Fred is alive. So we're in state 1. And for part E, the actuary realizes that transition intensity from state 0 to state 2, mu 02, should be lower. Without doing any calculations, state with reasons whether the expected present value of the death benefits under the new pricing assumption will be lower, the same, or higher than the values obtained in part B, assuming that the other transition intensities are correct. For part A, we calculate the probability of transition from state 0 to state 1 over a period of time of length t as the integral from 0 to t of the probability that for a time period of length s the system remains in state 0. So it goes from 0 to 0. Now you may want to ask here whether we should indicate that it's continuous remaining in that state and indicate it with a line above 0, 0. But that's not necessary because there is no going back to state 0 from any other state. So that's okay. Then in an instant between time s and s plus ds, so instantly, the force of transition from 0 to 1, which is mu 0, 1 superscript, moves that system from state 0 to 1, and then for the remaining period of time of between s and t of length t minus s, the system remains in state 1. And again, you may ask, well, but could it go somewhere and come back? And the answer is no, there is no going back. From state 1 you can only go to state 3, and there is no coming back from state 3. So no need to be concerned about this continuous staying in this state. That's what we want, which makes the calculation kind of easier, because we know that we just need to add all the forces of that will take you out of this state and take e to the minus that force times the period of time, which we do in the next step. For 0, 0, for remaining in state 0, we just take e to the minus sum of the forces that take this system out of state 0 over a period of time of length s. So e to the minus sum of those forces times s. The mu 0, 1 force is 0.01, and then we have the same e to the minus sum of the forces, but there's only one force, from state 1 to state 3 over a period of time of length t minus s. Now we pull out the terms that do not have the variable s in them, and what is left inside is e to the minus 0.13 s. So we have the integral from 0 to t of e to the minus 0.13 s ds. And the rest is in front. But that integral is equal to a bar angle t at 13%, which is 1 minus e to the minus 0.013 t over 0.013. And then we just calculate these terms, multiply them out, and get what we want, 0.01 over 0.013, multiplied by e to the minus 0.012 minus e to the minus 0.025 t, multiplied by t in both cases. For part B, the expected present value of the death benefit paid upon simultaneous deaths is the integral from 0 to 10, well, 100,000, because that's the amount, times the integral from 0 to 10 times of e to the minus 0.06 t, which is a discount factor for the force of interest, times the probability of remaining in state 0 for a period of time of length t, and then being whacked by going from state 0 to state 3 by that force of transition, which we know to be 0.001. And the probability of remaining is e to the minus the sum of the forces that take you out of state 0, multiplied by the length of period of time over which we're doing this. So this, if you multiply it all out and sort it out, this becomes just 100 times the integral from 0 to 10 of e to the minus 0.085 t dt. And then that's just 100 times a bar angle 10 at 8.5%. So we use a bar angle 10 formula. Calculated, we get approximately 673.62949. And yes, it's very good to note that this is a bar angle 10, because this means you don't have to calculate the integral. Anytime you can avoid calculation of an integral, you should avoid it. In fact, Professor Bob Batten of Georgia State University, who's, I believe, now retired, used to say that on life contingencies exam, if you calculating an integral, you're doing it wrong. You're doing something unnecessary. For the second part of this, part B, the expected present value for the case of Fred dying after Molly, for the expected present value of the death benefit, well, the benefit is 100,000 times the integral from 0 to 10, the discount factor, e to the minus 0.06t, times TP01. So over a period of time of length t, the system transitions from state 0 to 1, and then instantly the system transitions from state 1 to state 3. And the probability of that is that mu 13 times dt. And we take this integral of all possible values of t from 0 to 10. Okay, so it's 100,000 times the integral from 0 to 10, e to the minus 0.06t times, well, we calculate that TP01 at the very beginning. We plug it in. The force is 0.012. So everything is given now. We multiply it out a bit, becomes 12 over 0.013 times the integral from 0 to 10 of e to the minus 0.072t minus e to the minus 0.085t. Of course, that's just a bar angle 10 at 7.2% minus a bar angle 10 at 8.5%. Then we just write out the formulas for them, do the calculation, we get 361.9809. For part C, the expected present value of benefits is the sum of the two amounts we calculated, which add up to 1,035.61 approximately. In order to calculate the premium, we calculate the expected present value of a unit annuity paid the same way as the premium is paid. So annuity per $1 of premium, which is a bar 00 plus 0.75 a bar 01, because after transition to state 1, 0.75 of original premium is paid. Okay, well, a bar 00 is the integral from 0 to 10 of e to the minus 0.06t times the probability of remaining in state 0 all the time, which is TP00, plus 0.75 times the integral from 0 to 10, a discount factor, times the probability of going from state 0 to state 1, I'm sorry, yes, okay, that's correct, from 0 to state 1 dt. Well, we know these probabilities, we calculated them before, so we plug them in. The first integral becomes a bar angle 10 at 8.5%. The second integral is a difference of A bar angle 10 7.2% minus A bar angle 10 at 8.5%, then it has a factor of 75 over 130. Then we combine the like terms and we get 55 over 130 A bar angle 10 at 8.5% plus 75 over 130 A bar angle 10 at 7.2%. Then we just use annuities formulas, calculate all, and we get 6.962533. And the premium is the ratio of the benefit to that unit annuity, and that's 148.74046. For Part D, the net premium reserve at time 5, given that only Fred is alive, is calculated under a condition of a single constant force of decrement of mu13, which is 0.012, and under force of interest of delta of 0.06. And the reserve is 100,000 times A bar x plus 5 colon angle 5 with 1 above the x plus 5, so term insurance, present value future benefits minus present value future premiums, which is 0.75 p A bar x plus 5 colon angle 5. All this under constant force of mortality and interest. And the life insurance, term life insurance under these circumstances equals mu over mu plus delta times 1 minus e to the minus 5 times mu plus delta. And annuity is 1 minus e to the minus 5 mu plus delta over mu plus delta. That, and we're subtracting those things because everything ends after 5 years. And you should memorize these formulas. You can derive them by noticing that life insurance can be written as whole life minus deferred by 5 years whole life, so multiplied by pure endowment factor times new insurance, and it will all work out. And of course, insurance whole life under constant force, net benefit premium is mu over mu plus delta. And annuity is 1 over mu plus delta. In both cases, you really just have these multiplied by 1 minus pure endowment over 5 years. So we plug in all the numbers, we know them all, do the calculation and get 4,570.3137. For Part E, the expected present value of the death benefits under the new pricing assumption will be higher than the values obtained in Part B, assuming that the other transition intensities are correct. The reason why the expected present value of death benefit would increase is that a transition to State 2 would be less likely, therefore increasing the probability of moving to State 3 directly or via State 1, and resulting in a death benefit being paid with a higher probability. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.